In this video, we will take a look at a solved example on the CIR model, the Cox Ingersoll Ross model. The short-term interest rate, referred to as the short rate, is currently 4% per annum, and its annualized standard deviation has been estimated to be 80 basis points. We intend to use the CIR model to describe the evolution of the short rate, and we are given two of the three parameters which the CIR model works with. We are given the values of strength of reversion, denoted by K, and the long run interest rate, denoted by theta. The task at hand is to determine the third parameter, denoted by sigma, and also to determine the basis point volatility if the short rate were to increase from the current level of 4% to a higher level of 6%. Okay, so to solve this question very quickly, recall the SDE, the stochastic differential equation of the CIR model. This SDE verbally reads as something like this: the change in my short rate over a short period of time, a tiny period of time, dt, would have two components to it, a deterministic component and a stochastic component. The deterministic component, it stipulates that we have some kind of mean reversion going on with the strength of reversion measured or denoted by K, and the long run mean level towards which this mean reversion is happening being denoted by theta. Then the stochastic term involves the current level of the short rate. So this tells me that the volatility of changes in the short rate is not constant. It depends on the prevailing level of the short rate. And the functional dependence of the volatility on the short rate involves a square root. Okay, so if I were to use basic statistics and try and work out what the standard deviation of this dr sub t will be, then we can easily reason this out that this deterministic term would not influence the standard deviation of this drt. Okay, the standard deviation of this drt can be written as sigma times square root of the current observed level of the short rate. So as of time t, this entire thing is deterministic and therefore can be treated as a constant, that times the standard deviation of dwt, which we know is square root of dt. Okay, so standard deviation of the change in my short rate simply comes out to be sigma times the square root of the current observed level of the short rate, that times the square root of dt. So this tells me that I can think of this product, sigma times square root of r sub t, to be an annualized volatility, an annualized standard deviation, which is being scaled using the square root of time rule. This guy is referred to as the basis point volatility. It's the annualized standard deviation of changes in the short rate. Okay, so in the CIR model, we should remember this, that the basis point volatility is proportional to the square root of the observed or current level of the short rate, with the proportionality constant being the sigma. Okay, so we are given that the annualized standard deviation is 80 basis points. We know that this should be equal to sigma times the square root of the current short rate, which is 4%. This tells me that sigma is 0.0080 divided by square root of 0.04, which is 0.2, which means sigma is 0.04. Okay, so this is my first part of the question. If I were to now increase my short rate, the current level, from 4% to 6%, then the basis point volatility should become 0.04, which is my sigma, that times square root of the new short rate, which is 0.06, and which works out to approximately 98 basis points. Okay, so B is the right answer. Okay, so this video was about understanding the basis point volatility and how it depends on the level of the short rate in the CIR model.